Swayam Prabha. Digital India. Educated India.
Horizontal alignment part 1. After completing this lesson, the student will be able to identify various design elements related to horizontal alignment. The student will be able to appreciate the need and also understand the basis for providing super elevation at horizontal curves, and particularly the student will be able to understand the approach which is normally followed in India, that is the IRC approach. Let us look at various design elements related to horizontal alignment. They are horizontal curve, because a road can never be perfectly straight. A straight road is also not preferable from safety point of view. So, a road essentially consists of a number of tangents and curves. So, essentially or the curves are essential components of roadway. With curves, one should also understand the concept of super elevation and understand the basis for providing super elevation. So, super elevation is another design element. Then in most of the cases, whenever there is a horizontal curve, at both ends of horizontal curves there are transition curves in most of the cases. So, one should also understand why transition curves are necessary and understand the design basis, that means how the length of the transition curve should be decided. Then on horizontal curves, the rear axle and front axle, or the rear wheels and the front wheels rather, they do not follow the same track. So, often it is necessary to widen the road considering various aspects, mechanical requirement, psychological requirement. So, one should also understand the extra widening, why it is necessary and how one can calculate the required extra widening for a given road. Then on horizontal curves, side distance is a major consideration, particularly the inner side of the curve should be free from all sorts of encroachment. There should not be any obstruction that may cause difficulty in terms of available side distance. So, some distance up to certain distance inside the horizontal curve, it should be free from obstruction. So, that is what we try to calculate, how much portion or how much length it should be free from obstruction. So, there actually the setback distance is meaningful. So, altogether horizontal curves, super elevation, transition curve, extra widening and setback distance. These are the 5 major design elements when we are talking about the horizontal alignment. Now, as I mentioned that a road can never be perfectly straight, even if it is possible to have a road which is perfectly straight, it is not desirable to have a perfectly straight road for a longer length from safety point of view. So, ideally a road should consist of a number of tangents and horizontal curves. So, here that is what is shown here in the sketch. This is the tangent portion of the road, this is also another tangent, and in between a horizontal curve is inserted, which is shown as green lines. So, this is the horizontal curve. So, we have tangent at both ends and in between a horizontal curve is inserted. Most of the cases, or for in fact for design purpose, always we use circular curve for this purpose or this stretch. Now, as shown here, this is the tangent and here there is another tangent. So, this angle we call it as deflection angle, denoted here as theta. Now, some of the do and don'ts, in fact, some of the don'ts here in this case, like should be fluent and blend with surrounding topography, short curves for small deflection angles should be avoided, curves in same direction separated by short tangents should again be avoided and replaced by a large single curve. Sharp curves should not be introduced at the end of long tangents. Compound curves should be avoided. When unavoidable, limiting value of ratio of flatter curve radius and sharper curve radius is 1.5:1. This is as per the recommendations of Indian Roads Congress. So, what essentially I am trying to indicate that horizontal curves are essential components of roadway. Basically, from one tangent to another tangent, in between we provide horizontal curve, which is mostly circular curve, but these are some of the aspects which we should keep in mind, particularly some of the don'ts, what we should not do when we are putting a circular curve in between two tangents. Now, with this background, let us try to see what happens to a vehicle when the vehicle is trying to negotiate a horizontal curve. When a vehicle negotiates a horizontal curve, the centrifugal force, it acts outward, and this centrifugal force, it act outwards through the center of gravity of the vehicle, CG of the vehicle, and the centrifugal force, we can write it like this. Say if P is the centrifugal force, then P equal to W by G V square by R, popularly m v square by R if m is the mass. So, W by G V square by R, this P is the centrifugal force. So, if a vehicle suppose is negotiating this horizontal curve, so this force is acting outward in the outward direction. W is the weight of vehicle, g is acceleration due to gravity, v is the speed of the vehicle and r is the radius. Now, you can see from this equation P by W equal to v square by g r. This P by W, this term, it is known as centrifugal ratio or it is also known as impact factor. So, what we understand, centrifugal force which is acting outward is W by g into v square by r as shown here. Now, this ratio P by W, it is known as centrifugal ratio or impact factor, and this impact factor equals to v square by g r, where v is the design or is the speed of the vehicle, g is acceleration due to gravity and r is the radius of circular curve. Now, this centrifugal force when a vehicle is negotiating a horizontal curve, this centrifugal force has two distinct effects. One is it tries to push the vehicle outward and another effect is it tries to overturn the vehicle about the outer wheel. So, both effects they have they may have unwanted consequence in terms of the safety aspects. So, let us see the effects are tendency to overturn vehicle outwards about the outer wheel, this is one effect, and then the other effect is tendency to skid vehicle laterally outward. These are the two effects. Now, let us see, try to understand the overturning effect. Let us consider that this is a vehicle with the CG of the vehicle located at this point. So, the centrifugal force P is acting outward. So, obviously, this is the outer edge and this is the inner edge of the curve. So, centrifugal force is acting outward, this is P, weight of the vehicle is acting like this W. Now, if we take the moment about this outer wheel, that means about this point, then the overturning moment is P multiplied by h, where h is the height of center of gravity of vehicle above the road surface. So, P into h is the overturning moment. So, this has the tendency to shift or to turn the vehicle about the outer wheel. Now, this tendency is restored by a restoring moment, which is nothing but this weight of the vehicle into B by 2. If B is the distance between these two wheels or the total width, then width of the wheel base, then the restoring moment is W multiplied by this distance. So, this moment P into h is trying to turn the vehicle about the towards the outer side, and this tendency is resisted by the restoring moment W into B by 2. So, in limiting case or under equilibrium, P into h should be equal to W into B by 2, that means overturning moment equal to restoring moment. So, in that case P by W, the centrifugal ratio or the impact factor is B by 2 h. So, this is one equilibrium condition, limiting condition. That means, if P by W is more than B by 2 h, then the overturning moment will be more than the restoring moment and the vehicle will overturn about the outer wheel. So, for safe movement, the centrifugal ratio or the impact factor must be less than equal to B by 2 h. In fact, equal to is the limiting condition. Now, let us see the skidding effect. Again, a free diagram is shown. The centrifugal force P is acting outward. Now, in the transverse direction, if we consider the equilibrium, then this P force is resisted by skidding resistance, which is shown here as F A and F B. F A and F B. Now, F A and F B is nothing but coefficient of friction, this is in lateral direction, that is small f, multiplied by reaction R A as indicated here and R B correspondingly. So, R A and R B in fact together is nothing but the weight of the vehicle which is acting downward, because this weight is balanced by R A and R B, reaction at wheel A and reaction at wheel B respectively. So, if we consider now the equilibrium, then this P equal to F A plus F B. Now, F A and F B is nothing but coefficient of lateral friction small f into R A plus R B reaction. So, there mean it is F into W. So, in this case impact factor or the centrifugal ratio limiting value P by W equal to F. So, if the impact factor or centrifugal ratio is more than the coefficient of friction F, then the vehicle will be skidding, because the centrifugal force will be more than the skidding resistance. So, vehicle will laterally skid outward. So, in order to have safe movement, this centrifugal ratio must be lesser than the coefficient of friction. So, in fact, it is equal to coefficient of friction just at limiting condition. So, preferably it should be lesser than the coefficient of friction. So, if we want the vehicle to remain stable and safe, then the vehicle should not overturn, should not laterally move outward also. So, therefore, P by W or the impact factor or the centrifugal ratio should be less than B by 2 h, and the centrifugal ratio should also be less than the coefficient of friction, but this coefficient of friction is in the transverse direction. Now, for a flat road in the transverse direction, the centrifugal force or the impact factor should be less than F, and it should also be less than B h, B by 2 h. Now, to counteract the effect of centrifugal force and to reduce the tendency of the vehicle to overturn or skid, the outer edge of the pavement is raised with respect to the inner edge, and this transverse inclination of the pavement surface is known as super elevation or cant. That means, earlier we considered a vehicle like this. Now, we have made an inclination of road surface in the transverse direction like this, an angle theta. So, a slope is provided to counteract the effect of centrifugal force and also to reduce the tendency of vehicle to overturn or skid. Then this transverse inclination is known as super elevation. So, super elevation equal to, we denote it normally by small e, it is equal to tan theta, where theta is this angle. So, therefore, super elevation equal to tan theta. Now, let us see the analysis. Let us consider the same vehicle again, where we have provided a slope in the transverse direction with an amount theta. So, that the super elevation is actually tan theta. Now, this P or the centrifugal force is acting outward or in the outward direction. So, if we now take component of this P, observe it carefully, along that inclined surface along F. So, then we can actually take it like this. Now, this component is actually P cos theta, and perpendicular to the surface, this component is actually P sin theta. Similarly, the weight of the vehicle is acting vertically downward. If we take the component parallel and perpendicular to the inclined surface, then this component is again added W cos theta, and in this direction the component is W sin theta. So, now if we consider the equilibrium, then this P cos theta should be counteracted or should be equal to W cos theta plus the F, the force what we mentioned earlier, skidding resistance. Now, this F is nothing but coefficient of friction small f multiplied by the total normal force. Now, what is the total normal force? Normal force here in this case is nothing but W cos theta, as we have indicated, this is acting vertically downward. So, perpendicular to the surface, this component is W cos theta plus this is the centrifugal force. So, this component of this centrifugal force is P sin theta. So, what is the total force acting in the normal direction is W cos theta, this component, plus P sin theta. Now, this total force multiplied by F. So, that is the total resistance. So, this F, which is nothing but small f into W cos theta plus P sin theta plus W sin theta, that is this component, together should balance this P cos theta component. So, equilibrium equation we can write it like this: P cos theta equal to W sin theta plus small f coefficient of friction into P sin theta plus W cos theta. Now, if we take this P sin theta component to the left hand side, then what we find, P into this cos theta minus this f sin theta equal to W sin theta, this component, plus f W cos theta. That is what remains. Now, if I divide both sides by say W, if I divide both sides say P by W, if we want to calculate, then P by W is nothing but sin theta plus f cos theta divided by cos theta minus f sin theta. So, P by W equal to sin theta plus f cos theta divided by cos theta minus f sin theta. Now, if we divide both denominator and numerator by cos theta, then P by W becomes tan theta sin theta by cos theta. So, it becomes tan theta plus f divided by cos theta by cos theta. So, 1 minus f again sin theta by cos theta. So, f tan theta. Now, because normally this transverse slope which is provided is not very high, it is a very small angle theta. So, therefore, this sin theta and tan theta and multiplied by f 1 minus f tan theta, this is practically 1 minus f tan theta equal to 1 or unity, because f tan theta is a very negligible quantity, because theta is small. So, tan theta itself is a very small quantity multiplied by the coefficient of friction, which is again a small value. So, 1 minus f tan theta is almost equivalent to 1. So, therefore, what we get, P by W equal to tan theta plus f, but tan theta is again nothing but the super elevation, what we normally denote as small e. So, P by W equal to E plus f. Now, if you remember that P by W or the impact factor is nothing but V square by G r, because basic equation was force was W by G V square by r. So, W P by W equal to V square by G r. So, if we replace P by W by V square by G r, then this becomes E plus f equal to V square by G r. This is the very basic equilibrium equation we shall use frequently in the subsequent discussion. So, this is the equilibrium equation. So, V square by G r equal to E plus f, super elevation plus coefficient of friction together should be equal to V square by G r. But in this case, this V is normally expressed as meter per second. If we express this speed in kilometer per hour and use the value of G, acceleration due to gravity, then it becomes V square by 127 r. Basically, the same equation, the unit of V is different. Here in this case, it is kilometer per hour, and we have already put the value of G inside the equation. So, then it becomes E plus f equal to V square by 127 r. So, this becomes the equilibrium equation. So, one can use either E plus f equal to V square by G r where V is in meter per second, or E plus F equal to V square by 127 R, where V is in kilometer per hour, and in both cases R is in meter. So, this is the basic equilibrium equation which will be used subsequently for super elevation design also. Now, let us try to understand the provisions for maximum and minimum super elevation. Maximum allowable super elevation is decided based on several practical considerations. What we are studying now or discussing now is the recommendations which is followed in India, or with the recommendations of the Indian Roads Congress. As per the recommendations, maximum allowable super elevation is 7% for plain and rolling terrain, and one can also allow super elevation up to 10% for mountainous terrain not bounded by snow. So, normally it is 7% for plain and rolling terrain, and it can go up to 10% for mountainous terrain not bounded by snow. If it is bounded by snow, obviously it will be again 7%. But this is the provision as per the Indian conditions. These are the recommendations as per IRC or the Indian conditions. We shall study later the recommendation of AASHTO, or the American Association of State Highway and Transport Officials. Now, there is a minimum super elevation. One may be surprised why there is a need for minimum super elevation, but one can recall the discussion earlier lessons about the camber. Camber is also a cross slope, super elevation is also a cross slope. So, both are basically cross slopes. The purpose of camber was the drainage consideration. From drainage consideration, we discussed the need about the camber. Now, super elevation, the purpose is something else. The purpose is to counteract the centrifugal force in a meaningful way. So, if we find that the required super elevation is very insignificant, in fact, it is lesser than the required camber, then actually the camber should be the minimum or the lower limit of the cross slope, because if we provide a cross slope even milder than the required camber, then there will be drainage problem and pavement will be damaged in due course of time due to several other reasons. We have discussed those things earlier. So, there is a limiting value even on the lower side, that yes, there is a maximum value which is 7%, it may go up to 10% for hilly region not bounded by snow, and on the other hand there is a lower limit. The cross slope should never be lesser than the required camber. Now, again camber, what should be the actual value, that will again depend on what is the rainfall, whether it is heavy rainfall area or medium rainfall area, and what is the type of surface that is used for the road, whether it is impervious surface or other type of surface, say earthen roads or gravel road. So, obviously, the requirement of camber will depend on all those consideration, but camber should be the minimum acceptable slope, and also there is a prescribed limit for the maximum slope or the super elevation. Now, there is a 3/4 assumption. This is again typical to Indian conditions. Most of the cases, if we consider Indian traffic scenario, most of the cases it is highly heterogeneous traffic. Fast moving vehicles, new technology cars, old technology cars, other passenger vehicles, commercial vehicles, and even the non-motorized animal drawn vehicle or hand driven vehicles are also used or using the same road space. So, what happens if we provide super elevation considering the design speed, then it will be convenient and safe for vehicles which are travelling at or near the design speed. Basically, they are travelling at very high speed, close to the design speed of the road. So, for them the super elevation will be absolutely fine and it will be convenient also for the vehicles, for that kind of vehicles. But the same road space is also used by slow moving vehicle. So, if we provide camber or provide super elevation considering the full design speed, then for slow moving vehicle it will not be convenient. So, now the question comes, should we design the road for the fast moving vehicle for the design speed? The answer is yes, because a road is designed for design speed. So, a vehicle travelling at design speed also must be safe. On the other hand, a vehicle should also be safe, or the movement is of vehicle should also be safe, even if the vehicle is not travelling at a design speed. So, considering both these requirements, the question then comes whether the super elevation should be fully counteracted, fully counteract the centrifugal force or to counteract a fixed proportion of centrifugal force. Now, in the former case, the super elevation needed may be substantial and it may not be very convenient for the slow moving vehicles, that is what is indicated. Even when a vehicle negotiates a flat curve, friction would not be developed to the maximum. So, this is again not a balanced design. Therefore, it is desirable that the super elevation should be such that a moderate amount of friction is developed while negotiating flat curves and friction not exceeding the maximum allowable value be developed at sharper curves. For flatter curves, assume some allow some friction or consider the friction value into design aspects. Now, with all this background, considering all these aspects, IRC or the Indian scenario, the practice is to consider 3/4 of the design speed and provide super elevation, rather try to provide super elevation based on the 3/4 of the design speed. So, instead of designing super elevation for the complete design speed, an attempt is made to design super elevation with 3/4 of the design speed. So, therefore, whatever we have got earlier, that equilibrium equation E plus F equal to V square by 127 R. Now, we design super elevation E considering 75% of the design speed. So, it is 0.75 V whole square divided by 127 R. So, which becomes close to V square by 225 R. So, that is what we try. So, we try to design super elevation considering 75% of the design speed. Now, we shall come back to this part again. Let us try to understand the concept of equilibrium super elevation. If we neglect the coefficient of friction, that means, if coefficient of friction is assumed to be 0, then whatever super elevation is required to counteract the centrifugal force fully can be given or expressed as V square by 127 R, because in that case F is assumed as 0. So, the basic equation E plus f equal to v square by 127 r. If we put f as 0, then v becomes v square, E becomes v square by 127 r. So, this super elevation is known as equilibrium super elevation. Okay. Now, for equilibrium super elevation, the pressure on inner and outer wheels will be equal because of the effect of super elevation, but this will result in a very high value of super elevation. So, normally we try to counteract the centrifugal force with the help of both super elevation as well as coefficient of friction. Now, since we are talking about the coefficient of friction, what should be the design value? Now, actually this friction factor or the coefficient of friction depends on a number of factors. For example, speed of vehicle, type of and condition of the roadway surface, type and condition of the vehicle tires, etc. However, for design purpose, IRC recommends a value of 0.15. So, this is the value 0.15 we should use for design purpose. Now, AASHTO recommends value in a range depending on the design speed. So, design speed from 20 to 130, the value of side friction varies from 0.18 to 0.08. So, this table is given in AASHTO. So, depending on the design speed, one can provide or take the acceptable coefficient of friction. Anyhow, today's our primary discussion is the approach which is taken, which is followed in India. So, mostly it is IRC 1. Now, super elevation is required basically when vehicle has entered in the horizontal curve portion, but in most of the cases wherever it is possible, wherever it is practically feasible, for smooth movement we provide transition curves at both ends of. So, therefore, when there are transition curves at both ends, then super elevation is introduced gradually over the length of transition curve. That means, at the beginning of at the end of tangent, super elevation is 0, then it is gradually introduced over the length of the transition curve. So, at the end of the transition curve or the beginning of circular curve, full super elevation is available. Then the same super elevation is maintained throughout the length of the circular curve. Again, at the beginning of the transition curve to the point up to the tangent portion, it is again reduced, and right on the beginning of the tangent it is brought back to 0. So, that means essentially the full super elevation is available right at the beginning of circular curve, and that is introduced gradually over the length of the transition curve. Now, if transition curve is not provided, in that case 2/3 of the super elevation is attained at the beginning of circular curve. That means, even if there is no transition curve, on the straight portion itself super elevation is introduced partially, and at the beginning of circular curve 2/3 of the required super elevation is attained. Remaining 1/3 is developed over the length of the circular curve. The primary consideration, the primary basis for this is, even if we do not provide transition curve, the natural path of driving also follows a particular pattern, a transition pattern in that way, because drivers suddenly do not rotate the wheels to match to the radius of the circular curve. This is done gradually. So, that means right from the tangent portion, when the vehicle is on the tangent itself, driver start steering the vehicle and it follows a natural transition. So, therefore, 2/3 of the super elevation is attained on the straight portion and 1/3 is on the curve. Now, ruling and minimum radius of horizontal curve, you know the basic equation E plus f equal to v square by g r. So, for a particular, if we know the speed, if we know the allowable super elevation, design coefficient of friction, we can find out what should be the minimum radius of the circular curve. That is what is shown here. E plus f equal to v square by 127 r. So, r is nothing but v square by 127 into E by f. So, if our r is more than this value, then we can provide required super elevation without any problem or the restriction on the speed. But there are two types of speed, ruling speed and the minimum speed. So, the radius corresponding to ruling speed is known as ruling minimum radius. The radius corresponding to minimum design speed is known as minimum radius. Now, let us take an example, say for ruling design speed and the minimum design speed values are 80 km per hour and 60 km per hour. So, calculate the ruling and minimum radius. So, we know that E is 7%, f is 0.15. So, ruling is V ruling, which is 80 divided by 127 into E plus f. E is 0.07, f is 0.15. So, accordingly we can calculate the ruling radius. Taking the minimum design speed, in the same way we can calculate the minimum radius. Now, steps for design of super elevation in the mixed traffic condition. I have already mentioned that we try to develop super elevation considering 75% of the design speed. So, if we take that, then E calculated is actually v square by 225 r. So, we calculate E using this formula or assuming 75% of the design speed. If the calculated E is less than the permissible value, say which is 7% for plain and rolling terrain, then whatever E we have calculated, we provide that value. If not, then we provide only the maximum allowable value, which is for plain and rolling terrain, let us say it is 7%, but then we proceed with step 3 and step 4. Now, what is step 3? In that case, we have to check for the side friction, whether side friction is adequate. Now, what we do? Check for the coefficient of friction developed for the maximum value of E as 0.07. That means, assuming super elevation as 7%, we check whether the coefficient of friction which is required to counteract the balanced centrifugal force is adequate. So, here we again do this formula v square by 127 r, because this is the total force which is to be encountered. E is already 0.07. So, we check the value f equal to v square by 127 r minus 0.07. Now, if this E value or the f value is less the permissible value, that which is 0.15, then overall design is safe. With 7% super elevation also, the overall design is safe, because super elevation and friction, side friction together can very well counteract the centrifugal force. Now, if we find that this is even more than the permissible value of 0.15, in that case we have to go for the speed restrictions. There is no other way normally, or maybe change the alignment and have a different radius. So, in that case E plus f equal to v square by 127 r, put the limiting value of E, put the limiting value of r. So, total is 0.022 for plane and rolling terrain. This equal to v s square by 127 r. So, if we know the r value, that for a given situation this is the r, we can easily calculate what is the permissible speed that will be safe on that stretch of the road, where we are providing maximum super elevation up to 7% or the allowable super elevation. So, either in that case we have to go for speed restriction or have the radius of realign the road with a different radius. Now, let us see this example problem where horizontal curve with 400 meter radius and design speed of 100 kilometer per hour. So, we calculate E as v square by 225 r, it is 0.11. So, it is more than 7% for plane and rolling terrain. So, we take the value of E, we check the value for f and we find f is 0.13, which is less than 0.15. So, overall the design is okay. So, we provide super elevation of 7% and overall E plus f, it can counteract the force. So, the design is safe. Now, let us consider another example problem where design the super elevation for a horizontal curve 1500 meter and 80 kilometer speed. In this case also with 75% design speed we calculate E, but this E is lesser than 7%, but it is also lesser than the camber. The camber value is 0.02. So, what we try to do, we try to provide the slope equal to camber and check whether the normal cambered section can be retained. Normal cambered section can be retained means in that case E is actually negative. So, E is minus 0.02 plus f the permissible value 0.15, that means equivalent thing is 0.13. Now, we check what is the requirement for the given situation. Now, centrifugal ratio v square by 127 r, we calculate it as 0.033. So, it is certainly lesser than 0.013. So, again the normal cambered section can be retained and still the design will be safe in this condition. Now, try to answer some of these questions. Derive the equilibrium equation E plus f equal to v square by 127 r. Question 2, for radius 200 meter, permissible E is 7%, f is 0.15, calculate the safe driving speed. Then for a road where the design speed is 100 km per hour, radius is 300 meter, maximum value of E as 0.7 and f as 0.5, design the super elevation and give your comments. Now, let me quickly try to answer some of the questions raised in the last lesson. Explain the basis for obtaining intersection side distance considering crossing maneuver from the minor road with yield control. Now, two things we have to do: length of the leg along the minor road. This is approach is similar to case A, that means no control, but minor road vehicle is assumed to decelerate to 60% of the speed, not 50%. So, accordingly the TA value or the time for to approach the major road is decided, and here it is assumption is that travel time applies for a vehicle that slows before the crossing, before crossing the intersection, but the vehicle does not stop. And length of the leg along the major road is decided based on the basis that sufficient travel time for major road vehicles to allow minor road vehicle to travel from decision point to the intersection and then cross the road safely. So, where this TA is known is the travel time to reach the major road. So, this component is understood. W is the width of the intersection and LA is the width of the approach. So, this is to be covered, how much time it will be required divided by the speed but speed normally we use 0.278 V minor, but here the speed is reduced to 60%. So, 60% of 0.278, that is why 0.167. So, length of the leg along the major road can be calculated as 0.278 into V major into this time. Now, compare length of the side triangles along the major road considering left hand maneuver for yield control and stop control. Basically, both approach is same. It is 0.278 V major multiplied by time gap for minor road vehicle to enter the major road. In one case, for stop control case, it is 7.5 seconds to 11.5 seconds depending on the design vehicle, but in other case it is 8 seconds to 12 seconds, half a second more. Now, why half a second more? Because minor road vehicle needs 3.5 seconds to travel from the decision point to the intersection. This is not required for stop control intersection. So, this is additional time for yield control. However, for yield control the acceleration time is 3 seconds lesser, because the vehicle do not stop. It is a turning speed of 16 km per hour. So, this is 3 seconds less. Altogether half a second more is required. That is why it is instead of 7.5 to 11.5, it is 8 to 12 seconds. The last question was, discuss the IRC recommendation for intersection side distance for uncontrolled intersections and priority intersections. For uncontrolled intersection, the area of clear visibility should be determined with respect to SSD, stopping side distance. If inadequate side distance is not available, then vehicles must be warned with appropriate speed restriction. So, stopping side distance is the major criteria, and for priority intersection, minimum distance along the minor road is 15 meter. Along the major road, time required by the driver on the minor road to perceive the gap and then complete the operation. So, total time taken is 8 seconds for this purpose. So, distance along the major road is 8 seconds travel at design speed. That way one can calculate it.